All right, welcome everyone once again to the set theory seminar. And today we have Will Boney from Texas State University. Great that we still have the virtual format, so I can hear from Will. Might be difficult otherwise. And he will speak today on building generalized indiscernibles in abstract elementary classes with set theory. Go ahead, Will.
Well, thank you, Vika, and thank you for having me and for coming. I wrote this title and this abstract and then wrote the talk, as you do, and abstract elementary classes don't really show up very much, but generalized indiscernibles do and set theory does. So that's, and things around abstract elementary classes do. So hopefully this will still be of good interest to people. So there we go. So the quick outline, which I guess you can sort of see at the top as well, is we're going to sort of motivate this with kind of this new perspective on an old theorem of Morley. I put this asterisk on new because it's really from like the 1980s, which isn't so new anymore. But then we'll kind of talk about this framework of generalized indiscernibles and trying to generalize the Erdős-Rado theorem, and then kind of focus in on this weird thing that happens with the class of ordered graphs. And this will kind of take us to asking about sort of large infinities and then moving beyond V. So yeah, we'll get going, and feel free to jump in with any questions or comments as we go. So Michael Morley was sort of one of the pioneering, I guess, model theorists, not models theorists, who kind of kicked off this whole project of classification theory by proving Morley's categoricity theorem. That's not what we're going to talk about in this talk. We're going to talk about one of his other theorems, still from that same era. A lot of good work right out of the gate, which is Morley's omitting types theorem, that the class of linear orders is minimal amongst large finitely accessible categories. And okay, this is sort of somehow supposed to be a bad joke because Morley never said anything like this, or at least he never said anything like this in 1965. I don't really know what he did. He might have later in his life. What Morley's omitting types theorem sort of classically says is that if you take any sentence in L omega 1 omega, if the sentence has arbitrarily large models and size bet omega 1 is enough, or even like cofinal in bet omega 1, then you can build order indiscernibles. So for any linear order, you can build a model sort of around I where I is an order indiscernible. And, I don't know exactly the history of this, but without sort of too much more work, you can extend this from L omega 1 omega to L kappa plus omega, where if you have models of arbitrarily large size, here the threshold, this Hanf number becomes bet sub 2 to the kappa plus. Then you can do the same thing of building indiscernibles. And so this is Morley's omitting types theorem. It's a great theorem. We use it in infinitary model theory in abstract elementary classes all the time. Right, I mean, one of the applications is exactly the computation of this, well, we just call it the Hanf number, this bet sub 2 to the kappa plus, where you often want to work with classes and guarantee they have arbitrarily large models. And one way to do that, and Hanf kind of gave a replacement style argument that there is some threshold, but with Morley's omitting types theorem, you get this exact computation because, you can take an arbitrarily large linear order. Once you can build these sort of models containing I as order indiscernibles, you really don't care about the order indiscernibles. You just get arbitrarily large models. So this is a great theorem. But I kind of want to start with kind of understanding this category theoretic phrasing. And this goes back to Mackay and Perret, who actually have the book sitting next to me, one of the great features of the Zoom talk. Accessible categories, the foundations of categorical model theory. So they sort of cast this theorem in this language, that the class of linear orders is minimal amongst large finitely accessible categories. And what minimal means is that if I take a large finitely accessible category K, then there's a faithful functor from linear orders to K that preserves directed colimits. That's their definition of minimality. Okay, and this whole story has been my weak attempt at a joke. In addition to chiming in with comments and questions, pity laughter is always appropriate if you think I've tried to tell a joke. Okay, so the goal of this talk is, right, so Morley, as interpreted by Mackay and Perret, tell us that the class of linear orders is minimal amongst large finitely accessible categories. And I'm really interested in like finding others of these minimal categories. And also I'm really interested like what you can do with them, but that's not really the focus of this talk. And kind of this is my justification for why this is a project that really interests me. I describe myself as like a model theorist whose interests sort of intersect set theory and category theory. And this kind of checks all those boxes. That there's some category theory here and these like nice Mackay-Perret style phrasings. The question of how we find these minimal categories is really tied up in set theoretic questions, starting with sort of combinatorial set theory and moving to like large cardinals and forcing. And then once you have these minimal categories, the sort of AEC model theorist wants to use these to do a bunch of different things. So before we kind of get, or I guess the way we'll start getting into these details is by, so taking this sort of classical statement of Mackay of Morley's omitting types theorem, looking at this category theoretic phrasing due to Mackay and Perret, and kind of trying to come up with like a dictionary between these two things.
Could I just ask a quick question?
Yeah.
So in your category theoretic rendering of this theorem, does the indiscernibility play a role at all?
Yes, very much so.
So that would mean you would like to also get a version of order indiscernibility, like for things that are not linear orders, or?
Yes,
like,
so that is exactly where this talk is going. Perfect.
Okay.
But first I want to kind of like go through how we get this order indiscernibility here, and then what we'll see is that just like changing one parameter kind of exactly gives us other types of indiscernibles.
Okay, great. Sounds interesting.
Yeah. So we're going to start with, I mean, maybe this is not category theory and model theory, maybe this is more notation. I just wanted to like shove it into this table. So right, the class of linear orders, we're going to denote K or stands for order. And your morphisms here are sort of order preserving injections.
Could I ask a question also?
Of course.
Coming back to your introduction. So you've stated Morley's omitting types theorem in terms of L kappa plus omega, but the name of the theorem suggests it's about omitting types. And I guess any L kappa omega sentence could be phrased in terms of some sort of iteration of omitting types. Is
yes.
that the connection there, or is there something else going on?
No, that's exactly it. This is a result that I think goes back to Chang, that any L kappa omega sentence, you can kind of, I mean, essentially you Morleyize, you add predicates for all of your formulas. And then the only part of saying that those act as desired that isn't first order is you focus on disjunctions. And so you're like omitting the type of something that satisfies our disjunct phi, but not any of the R phis.
Okay.
And this is also how it kind of relates to abstract elementary classes, in that what Shalaz, so I sometimes call that like Chang's presentation theorem, because we have Shalaz's presentation theorem that says any AEC, you can expand the language so it becomes just a class of structures that are omitting some types.
Okay, so it's omitting a large family of types, right, of this bounded size, bounded by kappa.
Yes.
Okay, thank you.
Okay, so here's our dictionary. The first one is just this notation. So finitely accessible categories, we should kind of understand those as L infinity omega axiomatized categories. Now this is sort of, there are going to be several times here, I'm not going to say things exactly precisely. This is sort of kind of good enough for the phrasing that we want to do here. Really what the result says, right, there's some modulos here, that if you take a finitely accessible category, whatever that is, it's equivalent to some L infinity omega axiomatized category. And then if you take some L infinity omega axiomatized category, it might not be finitely accessible because it might have models that sort of finitely accessible means essentially closed under all unions, but also generated by like finitely generated objects. And we don't always have that. But if you scholemize your L infinity omega class, axiomatized class, then it's generated by finitely generated objects. And that gives you something that's finitely accessible. And as we've kind of discussed with, why do we call it Morley's-Amitic types theorem? We're going to be okay with like expanding the language and scholemizing. That maybe more precisely how Mackay and Perret should have phrased this is that like it's minimal amongst categories that admit a faithful functor from finitely accessible categories. But thinking of it as sort of L infinity omega classes will be a good way to approach it. Large, this is just like category theoretic for class many models up to isomorphism, which also is equivalent to saying we have arbitrarily large models. And then there's an extra pause there. Mackay and Perret said minimality was that you want to find a faithful functor preserving directed colimits from K or into your class. And this faithful functor is exactly what in model theory we would call like a blueprint or some way of building order indiscernibles. So I want to unpack this last piece a little more. That sort of model theoretically, what is a blueprint, right? It's this way it's this sort of set of instructions, like a blueprint, for taking a linear order, and you've got a bunch of functions in the language, so you sort of formally close the linear order over those functions, and then you wonder which of those terms you've created are equal, and your blueprint kind of tells you exactly which terms are equal. And it does this in a way where if, they're all like sort of, all of the instructions of when terms are equal only depend on the ordering of the inputs. And so you get these order indiscernibles out. So how does this give us a functor? Well, so these instructions are like faithfully functorial. What does that mean? That if I take any map of linear orders I to j, the instructions, and I build my model based on I and my model based on j, well, like the instructions, the j model is going to have the I model as like a subset of it, because you're just following the instructions from phi on the image of I or on this copy of I. And faithfully just means that like this is where we use that I and j literally live inside of these EM models. EM stands for Aaron Fuchs-Mostovsky. That I and j literally live inside of there, and we've just sort of whatever map from I to j holds in the like linear order category is extended to a map of these models. So that's what it means to be a sort of a faithful functor. And that these instructions are finitely generated, right? You're taking terms and deciding when they're equal, but that just sort of depends on finitely many elements from the linear order at a time. So this functor sort of interacts really nicely with, taking unions or taking directed colimits. That if I build my EM model from like the infinite union of some increasing sequence of linear orders, well, that's going to be the same as if I took the union of the models built from each of the individual linear orders. And so that's what it means to preserve directed colimits, is that these instructions are finitely generated. And so, what Mackay and Perret observe is essentially that any blueprint generates a faithful functor that preserves directed colimits. And it even goes back sort of the other way. This was before I knew this much category. This is something John Baldwin and I figured out many years ago. But if you just put it in this category theoretic language, that essentially if you start with any sort of, if you take a set of indiscernibles in a model that's extendable, you can sort of turn this into a blueprint. And so we have exactly, maybe this is the observation, because that's cut off, that blueprints for order indiscernibles in some, L infinity axiomatized category K are exactly directed colimit preserving faithful functors from K or to K. And I add this thing that, like, if I write K or contains the finite linear orders, there's this technical condition that you want them to all be the same size, because you want them to all be like the Skolem whole given some common class of functions. And you can get rid of that with a little more work, but it's sort of a technical piece that's kind of worth ignoring. But so this is sort of the starting place for this study, or for this project. And so, yeah, some natural questions are like, can we replace KOR with some other stuff? If we've got these blueprints, what can we do with them? And then, of course, this is the set theory seminar. So what does this have to do with set theory? So far, it's all model theory and category theory. So that's what we'll talk about. Gunter, you're asking about like how to kind of see these as indiscernibles, which maybe I haven't written down explicitly. The idea is, and I'm on my computer without a touch screen, but maybe I can annotate this. Right, I have my like linear order I, and I want to take, I take two increasing n tuples, right? Call this A bar and B bar. And the classic view of indiscernibility, right, is that since they're both increasing, the type of A bar and the type of B bar should be the same. How do we get this from this functorial idea? Well, we take just the finite linear order n, and saying that A bar and B bar are listed in an increasing order tells you that you've got sort of functors that take the n element linear order to each of these. And so now, or not functors, these aren't functors. Sorry. These are embeddings in the category of linear orders. And so now we hit it with this, now that we take this thing that's in the category of linear orders, we hit it with this functor, and we have an embedding of this one model, EM n phi, which maybe should be written phi of n. And we have these two embeddings given from this functoriality of phi f and phi g into M, so that, right, we have the two images and A bar and B bar sit here, excuse me. But these two structures containing A bar and B bar are actually isomorphic, right? F and G are isomorphisms, so they lift to isomorphisms over here. And so everything that you can say about A bar is the same about B bar, because these two structures are the same. And maybe this is where we assume that we've Skolemized things as well. So that, yeah, that's maybe the key piece, that since we've Skolemized, really we just need to worry that every universal statement is the same. And so that's what we've arranged here.
And so if you were to, I guess my initial question was more about how would you generalize from linear orders to other structures? I mean, I can kind of see how you could make sense of being indiscernible for some other relational structure, like some trees or something like that, for example. Right. Like if you have two isomorphic trees that you can just change the parameters labeling them or something like that. Is that
That's
the
exactly
idea?
What we'll kind of talk about next.
Okay.
Right, so this is the wrap up. Right, so now we're going to move on to like generalizing the Erdős-Rado theorem and generalizing indiscernibles. So exactly as you say, we want indiscernibles not generalized, but generated or indexed by structures other than the category of linear orders. If you do this just model theoretically, the notation is really difficult to write out. So difficult it made me forget there's two F's in difficult. And like Misha Gavrilovich has some way of writing this using like the simplicial category, which is exactly the kind of coherence of, it's something about like you have a bunch of types, but they need to cohere in the right way. But it's just easier with category theory. They're like a blueprint for order indiscernibles, as we've said, is a co-limit preserving faithful functor from the category of linear orders to whatever class you really want to deal with. Right, and so instead we can fix a different category of trees, category of ordered graphs, and a blueprint is still just going to be the same. It's going to be a co-limit preserving faithful functor from script K to bold K. Pandy Cat is a character in Gabby's Dollhouse, which my 3- and 5-year-old insist on watching all of the time. So it has infected all of my life, and so now I'm passing it off to you.
Could I just make sure I'm getting my intuition going in the right direction here? I should generally think of the target category, the codomain of phi, as being some structures equipped with Skolem functions and maybe even Morleyized and whatever else might be done, so that I don't have to worry about embedding versus elementary embedding or any distinctions like that. But on the domain of phi, I'm just thinking about orders or whatever simple thing is. The orders are not being Skolemized or anything like that, right?
Right. Yeah, so the way to think about this script K, right? I use too many Ks here. But script K is sort of your index class. It mostly is probably some sort of simple class. It's probably gotten ordering, probably some universal class. Maybe there are some functions, but not really big. Your script K is something like an AEC. Or your boldface K is something like an AEC.
So the script K, I should think of like, I should pretend to be a combinatorialist in script K, and I should pretend to be a model theorist in boldface K.
Exactly. And so they're kind of mediated, or your AEC is mediated by some Skolemized version of your AEC. And that's, so when you build blueprints, you Skolemize first and build a blueprint in the Skolemized category. But when you actually use them, you want to be in your original AEC, because you might want to talk about something like stability or like the classification theoretic properties that are going to be destroyed via Skolemization.
Okay, thank you.
Welcome. So let's go back to me being able to change slides. Right, this is something I remember my advisor Rami Grossberg saying. The definitions can't be wrong. So this is a great definition, because all definitions are great. But when you actually want to say that your definitions are good and people should pay attention to you, you need to actually show that they show up. And so when it comes to order indiscernibles or order blueprints for order indiscernibles, this is exactly what Morley's omitting types theorem tells us, that you take T in L kappa plus omega. If T has arbitrarily large models or models cofinal and bet sub 2 to the kappa plus, I can build some blueprint from the class of linear orders into the models of T. I do this by first Skolemizing T, so it becomes just like a universal class. And then, yeah, we'll talk about the proof a little bit. And this is where set theory starts to really come in. Because, right, when I talk about AECs, I kind of, and L kappa plus omega, I'm in this realm of infinitary model theory. And this is the set theory seminar, not the model theory seminar. So I'm omitting most of the discussion here, but right, first order logic, of course, has compactness. And so if you want to to build indiscernibles, it's enough to look at finite things to piece them together. So it's enough to use Ramsey's theorem. But when you go to the infinitary world, you don't have compactness. And so you need the sort of infinitary version of Ramsey's theorem, which is the Erdős-Rado theorem, right? So for every k less than omega, if we want to find a kappa plus sized homogeneous set for some coloring of k tuples, we have to start with a set of size bet sub k minus 1 of kappa plus. So how does this proof work, or what is the dream? We're going to go back to our model theoretic view. So we're thinking of, we start with some big model M, and we want to find some indiscernibles in them. And so we take some tau structure M, we take some big set X, it's already been skolemized, and we want to build phi by finding k indiscernibles for each k, and sort of like a coherent set of these. So base case k equals 0, 0 indiscernibles are anything, because you're just saying formulas with no parameter, the order doesn't matter. Okay, great. So you take xk, that's some large set of k indiscernibles for the induction set. Our coloring, right, we want to use Erdős-Rado theorem, we're going to use a coloring. We color the k plus 1 tuples of xk by their type. So if they have the same color, they have the same type, and they satisfy all the same formulas. I guess I should say here, their type when they're listed in an increasing ordering. So not k plus 1 tuples, but k plus 1 size subsets. Xk is big, so we can use the Erdős-Rado theorem to find a homogeneous subset for this coloring, and these homogeneous subsets are exactly k plus 1 indiscernibles. Iterate omega many times, and we're golden. We'd like to figure out, right, we started with something big, we'd like to figure out what that is. Maybe from how I've stated these theorems before, you already know that big should be bet sub 2 to the kappa plus, but let's see where that comes in the proof. And so what do? We want to shrink xk into a homogeneous xk plus 1. So to apply the Erdős-Rado theorem for a k coloring, maybe I stated it, maybe my indices are off here. Yeah, my indices are off here. I mean, no, this is right, because you're doing k plus 1 tuples, so I need the size of x sub k to be at least the size, or bet sub k of the size of xk plus 1 plus, but this is bad because that means I take a decreasing, the infinite sequence of sets decreasing in size, and this is actually like an ill-founded set of cardinals, which I don't have to tell the set theory seminar that this is bad news. So that's why I called this like the dream construction, because this is like morally what you want to do. But to actually make it work, you just need, it's the same idea, there's just like a lot more bookkeeping. So instead of like a single linear decreasing chain of xk's of length omega, you build like a tree of height omega that doesn't have any cofinal branches, but you need like so all the branches kind of die out, but you can get, so it's well-founded, but you can get as high up as you want. And there's a lot of bookkeeping here. Actually, Rositzky has this really nice argument that makes this tree idea explicit in a way that kind of gets rid of a lot of the technical bookkeeping. There's this other way, and this is, I think, Shalaw's favorite way, although I like it less, where you actually just like move to an ill-founded model of set theory, and you do this argument, and then you're fine. And the thing you end up with is like absolute between these from this ill-founded model, but I don't really like that for various reasons. But so when you do this technical bookkeeping, you need to start with bet sub 2 to the tau plus, where tau is the size of your language. And that comes into how many colors you're using, because if your language is of size kappa, or if your language is of size tau, then there are 2 to the tau many colors when you do this coloring by type. And then this bookkeeping means you sort of need to pump it up to this bet 2 to the tau plus. Okay, so now that's how we get indiscernible order indiscernibles using the Erdős-Rado theorem. And so how do we define generalized blueprints? Well, we're going to use, so in first order logic, you use Ramsey's theorem to get order indiscernibles. And they have this whole theory of generalized indiscernibles that I'm very jealous of, that I want to mimic. And what it turns out is you need like a structural Ramsey's theorem. And classes of finite structures with a structural Ramsey theorem are called Ramsey classes. So I want a structural Erdős-Rado theorem. So I'm going to use the name Erdős-Rado class. And so this is just a class, an index class where you can always build blueprints out of. There's some fine details that we're missing here from the category theoretic version, but this is sort of enough. And to actually build these, we need some structural version of the Erdős-Rado theorem. So we want to take something like ordered graphs, this is the one we'll talk about a lot, and think about coloring large infinite ordered graphs with some colors and trying to find sort of homogeneous subsets that are also large. But there's sort of a cautionary tale that kind of tells us that some extra care is needed. And so we're going to start with K2 OR, which just stands for two linear orders. So it's, yeah, the class of two disjoint linear orders, I0 and I1, and maybe just to give it the universe a linear order, you say everything in I0 is less than everything in I1. And I'm going to take an element of here, and I0 and I1 are probably really big, and I'm going to define a coloring where it's a coloring by 3 colors, but I only use 2 of them because I forgot to correct this slide, where I take I and J, and I color them 0 if they're from the same part, both from I0, both from I1, and I color them 1 if they're from different parts. And what I want is a big part of these linear orders that's homogeneous. Okay, but there are some problems here because, well, one, if I just talk about cardinality and I say I want a, two linear orders of big where the cardinality is big, I guess I could probably do that, but that kind of forgets that I'm in this category of 2 linear orders. So the first thing I want to say is that I want both parts to be kind of big in the homogeneous subset. And this is going to, in our definition, correspond to saying that some degree of universality. And the other thing that I might observe is that there's actually no homogeneous subset of this, strictly homogeneous subset, that contains infinite sets from both. Because anytime, I have I0, I have I1, if I've got big parts from both of these, well, I have like 2 things in I0, A and B, and 1 thing in I1, right? I've already got both colors represented because A and B are in the same one, so they get color 0. A and C are in different parts, so they get color 1. So I can't get true homogeneity. And the reason for that is I've sort of used the type of the elements in this structure to do the coloring. And as I add more structure to my classes, more than just a linear order, I can always do that. I can always use the types to help me with the coloring. And so what I'm gonna ask for is some notion of type homogeneity, which is, and we'll maybe, is this on the next slide already? Yeah. Where I'm going to ask for type homogeneity, where the coloring depends only on the type of the input. And so for this structural partition relation, we give this sort of Ramsey style arrow relation. I have this great quote from Heinal and Larson. I think this is from their partition relation chapter in the handbook of set theory, just saying how great the partition relation symbol is. It's a great one. And so, oops. what we're going to say is this holds if given any lambda big structure M, where big here really probably means less than lambda universal. So it contains a copy of any less than lambda sized structure in the class. So I have some lambda big M and some N coloring by mu many colors. Sorry, using my mouse and scrolling. I can find some kappa big N and an embedding from N into M that's type homogeneous. Normally you would ask that right, there's only one color represented, but again, we want to say that I have some tuple from N. There's maybe more than one color in the output, but if I look at the type of that input, there's only one color per type. Okay. And then in the same way that the Erdős-Rado theorem, which you think of as like, right, so the Erdős-Rado theorem is this kind of structural partition relation for K being the class of linear orders. And so, yeah, maybe this should say, right, so the following combinatorial statement suffices to show that K is an Erdős-Rado class, that we can build blueprints out of it. And it's basically what Ramsey's theorem says, that like, given any, fix all of these things on the right-hand side, you want to find a lambda big enough to make this partition relation hold. But of course, now these are infinite cardinals. And the argument is sort of morally the same, that you do kind of the same, I mean, you do a lot more bookkeeping, but you do the same kind of bookkeeping to try and like imitate this ill-founded dream proof. It's a lot more bookkeeping, but it's, you know, one of those things that happens when you spend a lot of time staring at like a very complex proof, and you eventually get to that point where it's like, oh yeah, I understand why you're doing all of these things. Then when you like change things, it's like, oh, you make the obvious change. And so yeah, so if you spend enough time staring at Morley's omitting types theorem, the proof of this would be clear, but you have to spend a lot of time staring at Morley's omitting types theorem, maybe. But it's the same kind of argument. Typically, this threshold that you get, right, in the Erdős-Rado theorem, it's like bet sub n-1 of kappa plus. And in the examples we'll see, typically you replace n-1 by some polynomial. So like bet omega of kappa plus would work for all n. And as long as, you know, there's a lot of kind of leeway that will always kind of give you the same sort of Humph number cutoff that we saw from Morley's omitting types theorem. And definitely whenever you have any polynomial, you get the same thing as before. And there's only one of these examples we'll see where you are doing anything other than just like taking a polynomial. But okay, maybe let's look at some examples. So, right, we saw this example where you have two linear orders. You can do this with like any chi. You take chi disjoint linear orders. Again, so you put this in some language, but there's an old result of Erdős, Heinel, and Rado that shows that that we have this nice structural partition relation. And right, what you need, this polynomial is n times n plus 1. So I should say that like the Erdős-Rado theorem is known to be tight, that if you anything less than bet sub k-1 of kappa plus will not work. Most of these other ones are not known to be tight. They're just sort of, that's what works, and maybe people are not quite as interested in coming up with these, I don't know, Sierpinski style counterexamples. Okay, so you can take chi-linear orders, you can make this a little fancier by convexly ordered equivalence relations. Morally, what this is instead of having a fixed chi that indexes your linear orders, you have like a linear order that indexes these other partitioned linear orders. And you can, I guess I should pick between CEQ and CER, but you use this Erdős-Heinold-Rado argument multiple times, and you can show that this has a structural partition relation. You can also do this for the class, or you can also show this for the class of well-founded trees. This is a result of Grunhut and Schalah. I like to mention this one because here, this left-hand side is very, very big. It's this bet sub 1 comma n, which, so like I said, this Hanf number, this map kappa to bet sub 2 to the kappa plus is, yeah, we do that all the time in sort of infinitary model theory. And this bet sub 1 n function, rather than iterating starting with the map kappa to 2 to the kappa, and you iterate that n times, here you start with the map kappa maps to its Hanf number bet sub 2 to the kappa plus, and iterate that n many times. So it's much, much bigger than these other cardinals that we're talking about. Gunther, you're asking about trees. So if you take some trees of finite height, and you look at this language, Schalah has this nice partition relation that is exactly here. There's some polynomial k and m. I think he gives a bound for it. It's in like the back of his first order classification theory. But the point is that bet omega would work here. And so one of the interesting things is, right, so I'm talking all about these structural partition relations. But again, the goal in my mind as a model theorist is not the structural partition relations specifically, but using them to build these blueprints. And so if you move from finite height to height omega, there's no combinatorial sort of partition relation here. But for this original goal of trying to build blueprints, you can still build blueprints indexed by trees of height omega by sort of taking every tree of height omega and saying, I can write it as like a union of n height trees. And as I go through my laborious bookkeeping, I start with a tree of height 1 and kind of interleave my find k indiscernibles, or find 1 indiscernibles, and then expand the tree to be of height 2, find 2 indiscernibles, expand the tree to be of height 3, find 3 indiscernibles, and you sort of interleave these two constructions and you build blueprints for trees of height omega. And then, yeah, so these are a bunch of examples. Sorry, one of my Zoom bars is in front of where I'm keeping track of my slides. Yeah, so I mentioned that there are a lot of applications. Again, this is speaks to the model theorist in me, and this is the set theory seminar. So maybe I'll kind of, well, there's only one slide on this right now, but just sort of mention these. The second one first. One of the really neat things is that, right, infinitary logic and model and AECs in general massively fail compactness, right? You leave first order, you really don't get much compactness. But kind of my interest in these blueprints as a model theorist is that they give you some fragment of compactness back. That if you have something, if you're in one of these EM models and you have something that, you know, it's kind of generated by finite sets, or maybe phrased another way, if you have some behavior of a structure, right, what's one thing you want to do with compactness? You have behavior in some structure of size kappa. And I want to show that that behavior happens in structures of lots of different sizes. And you kind of want to port behavior around between cardinals. Well, you can do that with indiscernibles if you kind of start with behavior in a big enough structure. You take whatever behavior it is and you generate some indiscernibles from it. This is where we use some of these more model theoretic particularities of this blueprint, this Erdős-Rado class definition. You sort of take that property you want to copy, make it part of your blueprint, and then you can plug in whatever size input you want to your blueprint to make it appear in a bunch of different places. So I have a paper on this called Indiscernibles classes. And one of the things that I do in there is there's sort of this classic first order logic result that if you're strictly stable, that means that you're stable in some lambda, but you're unstable in all cardinals lambda to the omega greater than lambda. And in fact, the thing that you prove in first order logic is that if you're unstable in some cardinal like this, you're unstable in all cardinals like this. And that's a compactness argument. You build what's called like, you take your instability in one place like this, you build a Shallah tree where you have different types indexed by a tree of height omega. You copy that around to different lambdas, and if you're, or to different kappas, and if you're in some other kappa where kappa to the omega is bigger than kappa, well, each branch through this kappa to the less than omega tree gives you a different type over a domain of size kappa. And so you get the instability at all kappa to the omega greater than kappa. So this is sort of very broad strokes, but the point is, since we know that omega height trees are an Indiscernibles class, you can mimic this proof using omega tree indiscernibles. Right, that's what we do. Where am I going? Right, these trees of height omega. So it kind of lets you, do compactness like proofs in AECs. Although you have to you have to throw the Hanf number in there somewhere. You have to say that I'm unstable in some lambda to the omega greater than lambda of size greater than the Hanf number. So that's sort of one application of it. Another, and this is going to become relevant when we talk about ordered graphs, has to do with defining lines in classification theory via indiscernible collapse. Right, so one way of talking about when a theory is stable is I have my class of linear orders, and I have some blueprint that goes to my models in my first order theory. And when I have this diagram, one thing I can do is I can imagine what happens when I sort of forget the linear order and I just look at the category of set. Okay, and then I can ask, can I sort of lift this embedding? Or can I find some blueprint here, call it psi, that makes this diagram commute? This is what in model theory we call indiscernible collapse. We're taking our order indiscernibles and we are forgetting about the order and wondering if they stay indiscernible. And Shallah proved that this diagram exactly characterizes stable first order theories. Well, he didn't, again, this is a la Mackay and Perret. And so you can prove the same thing for AECs. And so one of the motivations for me for looking at generalized indiscernibles is trying to do the same kind of indiscernible collapse characterization of dividing lines. And that brings us to ordered graphs, which, is what I call the elephant in the room, because we've mentioned it several times, but it wasn't on my list of examples. And especially when I start talking about indiscernible collapse, ordered graphs is like one of the first things you should think of, because after Shallah's proof that stability can be characterized by collapse of order indiscernibles to set indiscernibles, I guess this was many years after, Lin Sko showed that NIP theories, which is some other dividing line, can be characterized by indiscernible collapse from ordered graph indiscernibles to ordered indiscernibles. So yeah, I should mention KOG, OG stands for ordered graph. And so if we're thinking about trying to do classification theory for AECs, thinking about these generalized indiscernibles, this suggests a way of like talking about NIP AECs, where you say an abstract elementary class is NIP, no independence property, if every ordered graph indiscernible collapses to an order indiscernible. So for every blueprint from KOG to my AECK, I can sort of factor it through this diagram via this forgetful functor where I'm forgetting the graph structure on my ordered graph to just get an ordered set. As a great definition, again, definitions can't be wrong, but it's only like useful if there are actual like blueprints, like ordered graph indiscernibles, right? Otherwise, every AEC is NIP, and I haven't really done anything interesting. So we need to ask, are there structural partition relations for ordered graphs like the Erdos-Rado theorem? And the answer is maybe. And this is really where we're getting into the set theory, because all good maybes. This is all about consistency and independence, right? So what is known? So a bunch of people, right? We have this sort of finitary notion of Ramsey class. Ordered graphs is a Ramsey class. That looks grammatically weird, but I think it's right because it's really like the class of ordered graphs. And so we want to know now about like, but that's about finite structural partition relations. We want to know about infinite ones. Erdős, Heinel, and Posha showed that, right, we have something at like the countable level. Right, so if H is countable and we're coloring pairs, we're good to go. But Heinel and Komyath showed that it's consistent with ZFC that we can't do this for uncountable graphs. That there's a graph of size omega 1 that never shows up as like a homogeneous subset. Maybe I'll briefly kind of talk about the proof, but basically you start with GCH and you add a Cohen real. And this, you build a bipartite graph that sort of built from this Cohen real and some eventually dominating family in the ground law. Okay, so whatever. So consistently we have some problems, but then Shalab gave a dual result that it's consistent with ZFC that we do have these sort of partition relations. That for all ordered graphs H, for all kappa and for all n, there's some big enough G so that we have, so here, right, this is a different partition relation than I wrote before, but it should be interpreted sort of the same way, that any n coloring of the ordered graph G with kappa many colors, you can find some copy of H and G that's type homogeneous. And this also holds for colored hypergraphs, where really on G, rather than just an edge relation, you have some function from less than n tuples into some fixed cardinal theta. Right, and Heinel proves something else in ZFC, but it's only for finite things, so it doesn't really directly give us what we want. And so we started with a combinatorial question. The answer was maybe. But again, this wasn't really the question we wanted about. So we want to look at this proof and get some more information. And this is where we start to talk about sort of large cardinals and forcing extensions. But how does Shalab's proof go? You start with GCH to have some nice combinatorics or continuum function combinatorics at the beginning. You come up with you fix some mu and you come up with a forcing poset P mu that kind of, right, we're trying to prove something for all graphs, that for all graphs, there's a bigger graph that plays nicely with it. So your forcing P mu is going to add a graph G that takes care of all graphs smaller than mu. So it's a really nice function. It really just consists, you fix some big kappa, and you're adding like, yeah, you're just adding, forcing to add a graph of size kappa mu by less than mu sized approximations. And this sort of means that you really get some sort of like, not homogeneity result, but like end homogeneity result. But once you get a bunch of like end homogeneity results, you can string them together into a homogeneity result. and you take all of these forcings for different kappa mu, you Easton support, or you iterate them to get these sortives everywhere, and you string the sortives together to get the actual coloring result. Okay, and so now we're gonna sort of take a look at this result and look how it interacts with, some large cardinal stuff and some forcing. So looking at large infinity, what we want to use is kind of large cardinals to get rid of the necessity of forcing, or like the use of forcing here. And so what we're going to do, I don't know how much this counts as cheating. I don't normally use Laver indestructibles, but if you take Laver indestructible supercompacts, this forcing result tells you that you get just sort of like a Ramsey cardinal style structural partition relation for ordered graphs. Right, so you, you do this forcing to get the existence. So you have your supercompact kappa, you force the existence of some G star that gives you the partition relation that you want. Since you did this indestructible forcing, it's still super compact. Then, you take some coloring. You take some coloring of your less than kappa universal graph of size kappa. And you sort of use this to, right, you know that G star is this graph that has your nice coloring results. So you kind of port the graph over there and get sort of a less than kappa sized homogeneous sets. And the key is that this directed closed forcing guarantees that enough of these pieces are still in the ground model so you can use your universality. And then you have a bunch of, you can do this for any sort of less than kappa sized piece. And then you can use the tree property to string these together into an actual kappa sized homogeneous subset. Okay, and so what does this tell you? That there's a nice partition calculus for the class of ordered graphs from large cardinals. That if kappa is Laver, is indestructibly super compact, then it also satisfies this sort of Ramsey style partition relation. And this would let us build partition relations if we had an AEC with models of size at least this super compact. Okay, and we could do this, right? Shalah's forcing is about these like ordered graphs, but the key is anytime we can force this partition relation in this mu directed closed way, we can do the same argument. And Shalah and I currently have sort of a work in progress to figure out kind of exactly what those classes are. And so this is how we get partition calculus from large cardinals. But we can do a little better. Well, a little better for the model theorists, maybe not a little better for the set theorists. Because again, it goes back to this idea that the model theorist in me doesn't really care about the structural partition relation I've been talking about. It cares about blueprints. And so you want to ask, what are blueprints? So, right, it's some definable class functor, but it's generated from some small set. I wrote k to the less than mu here. But in all of the examples we've been talking about, you should really probably think of mu as omega. So you take all of these like finite linear orders or finite ordered graphs or finite generators of whatever index category you're thinking of. And all you really care about is the value of the functor on those finite objects. And so even though you need to go up to like 2 to the mu plus, or maybe even higher, depending on the size of the language of the AEC, the blueprint itself sort of as a set exists much lower down. If you do the kind of model theoretic view of blueprints, this is a little easier to see. they're really just like functions from types over the empty set in some language to types over the empty set in some other language. So these are very like low rank objects. And so we can go back to this theorem of Shallah and say that really, even though he said it's consistent that these partition relations hold, the classes themselves, you can actually, right, it's only consistent that the partition relation holds, but it's a ZFC theorem that you can build blueprints from. I say almost, this almost means that you're missing a few of the like technical pieces from the model theoretic definition, but still very good. So how do you do this? You kind of do the forcing that Shallah did in the previous theorem to kind of set everything, to make ordered graphs combinatorial Erdős-Rado classes. That means that this structural partition relation holds. Right, all these forcings are sufficiently directed closed, and Easton support iteration preserves this sufficient directed closedness. Now in the forcing extension, right, your AEC is still an AEC, or at least it still admits a faithful functor from a finitely accessible category. And so I can use this generalized Morley's omitting types theorem to build blueprints like, using this combinatorial relation. But since these blueprints are actually like small objects and sufficiently directed closed forcing doesn't add new subsets to V, small new subsets to V, this blueprint is actually in the ground model. And okay, so you need to verify that it's actually a blueprint and does all the things. This is called properness, but this verification is just delta one in the parameters. So it passes from the forcing extension. Right, it's just like, if you think of it as a function from types to types, you're just saying that they go here in the right way and stuff like that. So even though you have to force to get the combinatorics, you get the blueprints in the ground. And this is really great. And this is sort of one of the reasons that we're trying to figure out what other classes can you force to make these partition relation hold, because that would give you a lot more classes that you can build blueprints from. And so this sort of sets up some questions and work in progress. And like I said, right, where can you go beyond ordered graphs or colored hypergraphs in terms of classes that you can force to make this partition relation hold? Then once you have more of these classes you can build blueprints from, this sets up a lot more of how much of this kind of first order structure or first order map of classification theory and dividing lines can be translated to AECs solely through the language of indiscernible collapse, and what can you do with this? And then maybe this is not the best audience for this question, but I think that whenever you see like forcing used to prove a ZFC result, it's kind of like a natural question, like, did you really need forcing? Could you remove it? So I wonder if you could do that for these sort of ordered graph blueprints. Yeah, thank you.
Thanks very much, Will, for your great talk. Questions? More questions from people?
Yeah, I have a tangential question.
Yeah.
Came in this last bit. So suppose I have an AEC, and then I do some forcing somewhere. Then that class, taken literally, is not going to be an AEC, most likely, because it's not going to be closed under unions of chains that go off in some wild direction in the forcing extension. But from the point of view of the forcing extension, can one say can one give some nice properties that AECs are going to have after you force?
So your question is kind of, can I define like some mantle version of an AEC or something, of like a class that was an AEC before some forcing?
Yeah, I guess that's one way to view it.
Okay.
Or can one define the notion of let's say a weak AEC, such that I guess every AEC is a weak AEC, and being a weak AEC is preserved by forcing.
So let me give a sort of another way that you could talk about AECs with forcing. So, right, let me draw. Ernest Schimmerling once called something like this, like the only picture you draw in set theory, but I'm going to cut it off a little bit. So this is supposed to be my AEC K, right? It doesn't go all the way down to the point. So it's not the set theoretic universe. And you have at the bottom here the Lowenheim-Skolem number of K of the class. And that's kind of, you know, the size of your theory and the smallest models you've got. And so one way to kind of deal with forcing in AECs is, or so one way to describe an AEC, right? It's formally a proper class, but it's generated by set much information, right? You restrict it to models of size Lowenheim-Skolem number, whose universe is some cardinal, or whose universe is that cardinal. And you look at the embeddings between them, and then if you close that class under arbitrary directed co-limits, you're going to get the AEC K. You can sort of take your AEC, slice it down to a level, and then like regenerate everything above it.
Oh, I see. So what you're getting at is that although I may have messed up the AEC-ness of my ground model thing up high, if I've retained this bottom level, the Lowenheim-Skolem number, then the forcing model sees that and can use it to generate its version of what should be called the same AEC, except it's got more models.
Yeah, it's like the forcing extensions version. And what's going to happen when you do this is you're just going to get like at most a wider class.
Yeah, so this is sort of analogous to what happens in descriptive set theory, where if you add a real, then the Borel sets are all messed up.
Right.
But the code for the Borel sets is still alive and just generates a new Borel set.
Yeah.
Okay, so with that analogy, yeah, I guess that means this situation is as good as what we are familiar with in Borel sets, and therefore I should be happy with it. Yeah, good, thank you.
The only thing better than you should be happy is that if you're actually happy.
I mean, one way to cheatingly answer the question would also be to say the weak AEC is something that is an AEC in some ground model, right? That would be preserved by forcing. But of course, that's not what you have.
And I mean, I'm guessing and I would have to be better at forcing to make this precise, but I'm guessing some version of this weak AEC would be like, I've got these generators down in LS of K, and my weak AEC, this green part, is not every directed co-limit that I get, but it's the collection of some directed co-limits that's closed under submodel. Yeah, you could maybe, and because the kind of way that you're making this wider is essentially you're adding new like index sets for your directed co-limits.
Okay.
Could I ask so I have a silly question. So when you talk about this indiscernibility, the length of the parameters, the parameter list that you can plug into a formula is arbitrary less than kappa, or
no, it's still finite.
It's always finite. I see.
Yes.
Okay.
Because you want essentially right. This is where this we're thinking back to L kappa plus omega.
I see. Okay.
And you have a lot of problems on all sides if you try and move to L kappa plus omega 1. Right. Partition relations famously fail if you're coloring infinite tuples. Also, blueprints are really good at giving you models that have lots of automorphisms, but well orders are L omega 1 definable rigid classes. So you have lots of problems. I think, yeah, Rositsky has this paper. This is where he gives this really nice tree argument, where he kind of like, yeah, proposes this question of, could you, so we know linear orders isn't it, but could you define some, could you pick out some category that is minimal amongst your L omega 1 omega or L kappa plus omega 1 axiomatizable categories? And this argument I told you says that it has to be much more rigid than linear orders. But
Right.
I don't think he's successful in figuring one out. I think he's successful in ruling a bunch out.
Okay.
Tibor, I don't know if you remember this paper better.
It's been published. Usually was thinking about it for decades. I think he returned to it over and over again. He was fascinated by this categorical retelling of Morley's theorem. And my recollection is that he went back to work of Czech combinatorists, Vera Trnkova and related people, creating a category where no object has non-trivial automorphism. So it's very, very rigid. And then use that, just as you say, to say that if there is a minimal category of that type, it must be very freaky. Okay, well, this is not the way that he phrased it. I think it's been published at preprint, so we should be able to identify it. Sorry, I can't answer your question what exactly the conclusion was, but not very definitive. This is my recollection too.
Yeah, I became aware of this preprint in 2018, but I guess maybe it has a much older history.
Okay.
Any other questions for Will? All right, then Will, thanks so much again.
Yeah, thank everyone for coming and the great questions.